So welcome everybody. Welcome everybody to this afternoon session. I am Vincent Lam. I'll be chairing the sessions this afternoon. And just before we start, just a comment. Please mute yourself during the talks so we avoid background noise. And another thing, this is so the second conference of a series. We hope that there was a first event in Copenhagen 2 years ago, and proceedings were published. So, and we're thinking about doing the same. You can have a look here. I put the link in the chat to the volume published out of this conference, and we hope to be publishing also proceedings out of this conference. And now let's get started. It's a pleasure to have to welcome Owen Maroney from Oxford. He's a lecturer at Oxford. He is working in philosophy and foundations of physics, and it's really a pleasure to have him today talking about quantum theory and scientific realism. So please, Owen.
Okay, can my screen is my screen sharing working fine? Good. Okay, so my talk actually is like normally when we talk about quantum mechanics and theory and knowledge, we usually think about the limitations of knowledge, in fact, in what it says. I'm kind of scratching my head and wondering about whether or not some of the kind of analysis that we've got used to using in quantum mechanics actually is giving us more knowledge than we might normally previously have thought we have. So particularly, I'm going to be looking at some of the kind of foundational tests of quantum theory, and trying to relate them to perhaps the traditional arguments about scientific realism. So this is very much an exploration. It seems like a funny possibility that's been thrown up by some of the kind of analysis of no-go theorems in quantum theory. And I'm really at the stage of just wanting to actually explore, to what extent these connections could be made. So I'm putting that caveat out there. This is an exploration rather than a finished argument, let's say. So what the talk is going to be about, I'm going to kind of go over a very hand-wavy take on the traditional problems of scientific realism. So I'm not planning to get into a great deal of depth on there. I'm just going to use that to sort of set the scene for it. And then look at this kind of the ontological models view of quantum theory, which is this sort of framework that's been used to analyze different interpretations of quantum theory, no-go theorems about quantum theory. And there's claims about the ontological models approach that it allows what sometimes gets called empirical metaphysics, particularly in the terms of the Bell inequality, where it puts constraints on not just how we interpret quantum theory, but it yields experimental tests that somehow could be considered constraints on any future theory, even if the quantum theory itself is replaced. And it seems, well, if this kind of ontological models claim of empirical metaphysics can go through, then it seems that that does actually have some consequences for how we think about scientific realism and some of the traditional problems of scientific realism. So that's what I just want to actually explore, is like, to what extent can this claim actually be made through? What would a scientific realist get a reason to believe in as a result of this ontological models approach to quantum theory? And does it actually help with the problems of scientific realism? So to sort of set the scene, the problems of traditional scientific realism. And now, again, I have to say, this is a kind of very hand-wavy view of, well, what exactly is scientific realism? In an oversimplified nutshell, we could say that scientific realists are broadly committed to some variation on the theme of there are mind-independent facts, that scientific theories are to be understood as making statements about these facts, and that we can have good reasons to believe that these statements are true. And now all of these statements are, this way I put it, is definitely a lot more hand-wavy than the more very precise ways you will often get them in the philosophy of science literature, which is going into detail about scientific literature, where people are trying to make this much more precise. That's because I don't want to get into the precision of scientific realism. I want to look at specifically how these kind of claims can relate to the kind of claims we get in foundations of quantum theory. What's So I'm not going to, for example, go into the exact way in which scientific statements should be made in correspondence to mind-independent facts and worrying about correspondence theories of truth and so forth. And the only thing that I would call attention to is that it's the claim here is that we can have good reasons to believe these statements are true. So it's specifically about whether or not it could provide a good reason, not necessarily whether the particular arguments that I'm actually looking at do provide a good reason to believe the statements are true, but whether the kind of analysis could yield a new take on scientific realism. Okay, so the traditional argument for realism, let's say, then goes along the lines of scientific theories are conceived as being a picture of the way the world is. It's used to make observable predictions. And then, of course, if the prediction is successful, this is a reason to believe in the picture. Now, this last line in itself is both uncontroversial, I would say, but also not actually the key point. Certainly, if something makes predictions and those predictions are borne out, that is evidence for the thing that made predictions. To be actually a scientific realist, we know to go a bit further than that, that the predictive success is actually a warrant for the belief in the sense that it doesn't just provide evidence for the picture of the world, it's got to be the best explanation for it. It's that other attempts to provide explanations for those predictions, other things that make the same predictions, are not as good explanations. So this is the kind of best explanation or no miracles argument for scientific realism. So again, I'm rushing through this because the details of this isn't actually the main thing that I'm actually trying to focus on. I'm just setting the scene here of what we're thinking about. And the problems of this, though, is more interesting. So I'm going to say, well, there's two problems I'm kind of worrying about here, which are the problem of theory change, that past theories can be predictively successful, but nevertheless false. So, for example, 19th century atoms were indivisible by their very nature. 20th century atoms are not indivisible. So the things that 19th century atomic theory refer to don't actually exist. Now, this kind of maybe the scientific realist says that's not a problem so much because I can just, okay, I got the details of atoms wrong, but I can still believe in the existence of atoms, so that I don't have to actually get all the details about atoms right to think that atoms were predictably successful. But then there's more challenging problems like phlogiston and caloric and ether, where it's not simply that there's a false claim in the theory. The central terms of the things to which the theory is committed, we no longer believe even exist. So it's not just like we've got the details of phlogiston wrong. It's just there is no such thing as phlogiston. So any kind of empirical success that's a theory that the phlogiston theory had couldn't possibly be taken as being warrant to believe in phlogiston. So if any literally true reading these past theories was hopelessly wrong, how do we actually say that predictive success is a justification for believing in the theoretical commitments of that theory? So that's the sort of the problem of theory change. We now then are faced with our current theories, and we will say, well, if our current theories actually turn out to be incorrect, well, where's the guarantee? Where's any reason to believe that the empirical predictive success of our current theories is reason to believe in the theoretical entities postulated by our current theories? Okay. The second kind of big thing is the problem of theory choice, the underdetermination problem, which is, it's sort of related, but it comes up slightly differently. For any given set of empirical data, there are multiple theories that could produce that data. You can always sort of cook up alternate theories that will make the same empirical predictions. And this can come in a weak form where you've got two theories that might actually differ on future predictions, or the claim is that there's actually a strong underdetermination thesis that for any one theory, you can come up with a theory that makes different ontological commitments, but nevertheless predictably identical to it. And if that's the case, then which theory is the predictive success supposed to support? So the empirical evidence is not going to be able to tell you which of these two underdetermined theories you should actually be believing in. And of course, there's also the problem, even if you actually had some criteria to choose between them that was convincing, You can only choose between the theories you have available, or maybe actually the right theory isn't actually even in the list of the theories you have available. And even if you have a best explanation, well, maybe actually all of our candidate theories are wrong in very significant ways, and we just haven't discovered the correct theory yet. In which case, even if we had a way to break the underdetermination amongst a list of existing candidates, that's not going to help us. That still doesn't give us reason to believe that that best candidate is actually giving us an accurate picture of the way the world is. So that's the sort of traditional problems for scientific realism. Now, it's worth noting these aren't meant to be general skeptical doubts. My reading of how we should be interacting with these, they're not intended to deny, they're not arguments that are intended to deny that there are mind-independent facts, for example. They're challenges to the idea that predictive success warrants belief. They're challenges to the idea that the success of our current scientific theories gives us reasons to believe in the theoretical commitments of the theory. So the kind of standard responses there, of course, there's lots of responses out there. Mainly the realist responses lie in some form of restricting their commitment to the theory, to say that there's only parts of the theory that are responsible for the predictive success. And so we look for the parts of the theory that are responsible for the predictive success and only need to actually have a strong commitment to those parts of the theory. So this falls into different kind of things. So the more traditional entity realism goes for the sort of divide and conquer strategy of identifying the entities in the theory responsible for novel predictive success, and various other strategies to deal with underdetermination. A slightly more radical, the structural realists want to abandon all commitment to the entities of the theory and only try and extract the structure of the theory and claim that the structure of theory is what, for example, is carried over across theory change. Now, both of these are responses to theory change and theory change and theory choice problems. The anti-realist, of course, still has to actually say something about the empirical success of the scientific theories, and still has to actually tell a story about what's going on with theory change and theory choice. And these can, again, at a very oversimplified way, these can fall into, for example, trying to interpret unobservable terms in terms of operational terms, seeing phlogiston not as a commitment to the existence of a thing, but rather an operational set of procedures, just a label that applies to some sort of operational procedures. Or take the theory at face value, but just simply don't withhold belief about the unobservable. Say that only the empirical adequacy of the theory is all we need to look at. We only need to look at the predictions. And we can just say, well, we don't actually have the ability to gain epistemic access to the unobservable theoretical commitments of the theory. So we should just be agnostic about them. So that's really kind of, I'm sure there's a lot of people in the audience now that are sort of wincing at just how oversimplified I made all that particular dialogue. And there is, of course, a great deal of subtlety and nuance. The reason why I don't want to get into that subtlety and nuance is because the whole point of my talk is to say, well, what if we actually might want to take a different response? Is it possible to actually take a different attitude to this? What if, and this is sort of a little bit head scratching to try and make sense of to me, but what if there were empirical grounds to make commitments to unobservables? Now, that seems at first kind of strange because the whole point about predictions, you've got to make predictions about observables. You observe stuff, you make a prediction about the observables. Can you really, is there a way in which you can actually take empirical predictions to draw conclusions about unobservable entities without getting involved in theory change and theory choice worries? And at first sight, this sounds like it doesn't make any sense at all, I would say. But the no-go theorems of quantum theory perhaps have made claims like this. So maybe it's worth exploring if no-go theorems of quantum theory can provide an argument for scientific realism. So this is where I'm going to jump off, and this is what I'm going to start tackling. Okay. So first of all, I'm going to introduce the framework that's used to analyze the no-go theorems in this way that I'm going to suggest might actually give us a new approach to scientific realism. And this is just looking at the ontological and operational way of characterizing quantum theory. Now, I'm not going to say anything about quantum theory. I'm just going to look at the operational and ontological frameworks, because the part of the claim here is that these frameworks don't in themselves depend upon quantum theory, so they make claims, therefore, that will actually hold for any future theory, even if quantum theory turns out to be wrong. So the operational framework goes, suppose I have a laboratory here, and I've got large amounts of different bits of equipment in the laboratory, and I've got these three physicists, Penny, Terry, and Mary. Each of them has got a lab book with a set of operational instructions in them, and they have their labels that they apply for them. Penny labels her different possible sets of operations with a P, Terry with a T, and Mary with an M. So initially, Penny goes into the lab, and she, following her instruction booklet, she picks out one of the operational procedures and goes through it, and she plugs together some of the equipment in a particular way. And then she leaves. And she notes in her lab book which operational procedure she did in that case. Then Terry goes in. Terry further follows another set of operational procedures, well defined, changes various different things in the lab, and leaves again. And finally, and Terry also notes on that particular case which particular procedure he followed. Then Mary goes into the lab. Mary again does a further set of changes to the lab, moves things around, hooks things up a particular way. And then finally, Mary, unlike the others, notes some observation in her notebook, which we're going to label Q, some outcome she actually gets. Then Mary leaves the lab. And then finally, Terry, Mary, and Penny get together. And after they perform this operation a large number of times, they go through this cycle with all these different sets of operational procedures, these P, M, and T procedures, and they get together and they compare their notes, and they look at when certain particular combinations of operational procedures, P, T, and M, are performed, what's the relative frequencies with which Mary observed certain outcomes Q, the particular outcome Q. And that's it. That's the operational framework. So here we just have a set of procedures that are labeled PTM, some outcome that's observed, and the empirical data is we note after a large number of performing all sorts of different procedures that we hit these stable relative frequencies of particular outcomes occurring, given particular sets of procedures being performed. Well, they then go away and they parameterize this and they study the actual procedures and the relationships between them. And they don't just sit on that. They actually find that there are a set of interesting relationships amongst them. Particularly what they actually find in this case is that these relative frequencies can be put in this very interesting form. And this turns out to be quantum theory. And in this situation, how we interpret these things is that what we normally think of as the quantum state just is actually the label that Penny is using to apply to the operational procedures she's using to prepare a system. And U is just a label for the transformation that Terry is doing when he goes into the lab. And M actually corresponds to some sort of further procedure. And Q turns out to correspond to a projector within a Hilbert space. And the operationalist framework says nothing more about what the quantum properties phi, U, and psi represent beyond just they are labels that can be used to calculate the relative frequencies. And that's the sort of the very sparse, austere operational view. Ask no more than that. Okay, so some of us aren't happy with that and think that maybe there's something a bit more that can be said. Particularly what's sort of missing from this is actually any description of what was in the lab. So I'm just going to put another label for this. I'm going to introduce lambda. Initially, we've got a lambda 0. So when Penny goes in and moves around stuff, she changes the physical state of what's in the lab, the stuff in the lab, and then she leaves. Now, we're going to assume, I'll assume for the sake for generality, that Penny's procedures don't necessarily pick out an exact, distinct physical state, that there's some freedom available. Even classically, it would be hard to imagine that, you know, if you arrange the lab a particular way, that you guarantee there is exactly one and only one possible physical state. So what I'm going to assume here, and big assumption perhaps, is that when Penny prepares the lab, follows her preparation procedures in some particular way, what she actually does is produce some physical state in the lab with some probability. And that could mean that there's just some fine-grained detail that's not actually accessible, that's not observable, that Penny can't actually see. So then Penny leaves. Now what's left in the lab is just this physical state lambda. So when Terry comes in, Terry moves things around. Well, in the most general representation of this, we can suppose is this is a stochastic map. He changes the state in some way of the physical state in the lab and then leaves again. Now we could actually regard this as just being a different way of preparing the physical state in the lab. Okay, finally, Mary comes back into the lab at the end. Mary again performs further procedures, which result in something being actually observably different. Mary writes down that observably different thing, and we're going to represent this just by the probability that some observable consequence comes about following Mary's operation, given the physical state in the lab when Mary entered it. So in this case, the lambda is in many ways just meant to be a stand-in for everything that's physically relevant left in the lab between one scientist leaving and the next scientist entering. And that's it. It's just meant to capture that. That's all it's supposed to be doing. Of course, now when Penny, Mary, and Terry get back together, however, now when they gather up and analyze their relative frequencies, they're going to actually see this slightly differently. They're going to actually explain these relative frequencies in terms of this underlying probability distribution over the physical states in the lab. And it will have this particular structure. So here we have the ontological model's view of it as opposed to the operational framework, where we prepare some physical state with some probability, and then we mess around with another probability, and then we perform a measurement and we get an outcome. We perform a measurement on the physical state and get an outcome with some probability. So now the empirical data now has this additional term, which is supposed to be a representation of the way the world is, or the physical state in the lab. But of course, we've still got to get this to result in quantum theory. Now, it is actually a fairly mild assumption, because it's almost always possible to have the existence of something that's going to fulfill the role of lambda. Trivially, you can always do this by, for example, just identifying lambda with the preparation procedure. So you could, for example, come up with a model, an ontological model that would fulfill this by just saying, okay, so the preparation procedure just picks out an individual physical state. So now if we're saying, okay, psi is supposed to be the state that Penny prepares, we're just going to imagine she actually prepares a particular ontological state, a particular physical state. And then the transformation is just a transformation from one state to another. And then we have this stochastic process. So you can always actually, in the case of creating, when we have this kind of structure, you can always write something out here. It just might not be what you would expect to write out, and it might have some funny properties. So there's certainly the case that an ontological model will always be possible. But what kind of structure does it have? Is it plausible? That can't be answered. The more interesting point is that although an ontological model for any given set of empirical data is possible, many ontological models for any set of empirical data is possible. So although we kind of have this situation of a model, empirical data, and we're trying to come up with an ontological model to explain or account for the empirical results, this structure of it is generally going to be very undetermined. So it doesn't seem, at least, that this is going to help for the scientific realist at all. It says that a scientific realist theory is possible. It's always possible to come up with something, but that's not really helping with the theory change or underdetermination arguments, because the underdetermination argument is precisely that there's loads of possibilities. You're not, if we had one possibility, we wouldn't have a problem with underdetermination. We actually have too many possibilities. So that doesn't seem to be helping for scientific realism at all. Okay, but there is more. That this is not what the ontological models it was developed for. So the phrase ontological models was put forward by Speckens, but really building on the work of Bell and Koch and Specker and looking at hidden variable theories. So the framework itself was developed to analyze shared structure for all possible models of given experimental data. So the idea was not to come up with a particular ontological model for quantum theory. It was developed to actually analyze whether there are some things that must be held in common by all possible models of experimental data. So this comes from the sort of the traditional no-go theorems for quantum theory. So Bell's theorem said there's no locally causal ontological model. Or Koch and Specker theorem can be said there's no non-contextually valued definite ontological model. These no-go theorems don't directly analyze quantum theory. They derive some property from ontological models. Given some property, any ontological model sharing this property must have some empirical consequence. And then we use quantum theory to identify empirically viable situations where that property can't hold. But this is now, as in the classic case is the Bell inequality violation. The claim is if the Bell inequality is violated empirically, as it has been, then that's an empirical test of shared structure of all ontological models, so that no empirically viable theory in the future can ever embed local causality, regardless of whether or not quantum theory is in future abandoned. And this was described as empirical experimental metaphysics. Now, these have been negative claims. The question is, I want to know is, can there be a positive claim? Is there a claim that all future theories must include certain properties in their ontology? And if we can make a positive claim, not a negative claim, does this have some implications? Well, as always, when you pose a question like that, the answer is, of course, yes or no, obviously. So in this case, I'm going to be saying, yes, we can. So we have three views. The analysis that's been done on this, and I'm going to have to skip through. I've got a lot of technical detail here that I'm going to have to move through rapidly. But three views on the quantum state is looking at a way of actually looking at this, how we view the quantum state in these ontological models. One thing, as I said before, is we could just suppose that the quantum state is the ontic state. The physical state just is the quantum state. This is being called psi complete. The traditional wave function collapse interpretation fits into this method. If you add hidden variables, that's effectively saying, well, we've got extra structure to this. So a given quantum state actually has a large number of physical states associated with it. And that when you prepare some quantum state, you're typically getting some stable probability distribution over that additional structure or the hidden variables. So lambda is often associated with hidden variables, but it doesn't have to be here. And then, of course, the analysis of this very much was about advocating for a position called the psi epistemic point of view that said, suppose these probability distributions are overlapping. If the probability distributions are overlapping, then I had two different preparation procedures that correspond to two different quantum states according to the operational characterization of quantum states. But they actually could have produced the same physical state in the lab. And the claim here is that this would mean the physical state is not real. The quantum state is not real. The quantum state doesn't pick out distinct physical states. The quantum state is just a probability distribution and nothing more than this. Now, there are some limited models, constructed models of this. I'll get back to saying the significance of that later. Now, it's worth noting that this view of psi-ontic and psi-epistemic is not the traditional consideration of the quantum state. Perhaps traditionally a view on the quantum state is to view the wave function as being a calculational tool for predicting the results of experiments. That was the sort of operational framework. And the realist view of the quantum state was often to say, take a literally true picture of the way the world is, a wave function realist. Suppose there really is some physical object that is actually characterized by the wave function. So the psi-epistemic and psi-ontic views are slightly different to these. The psi-epistemic view is really describing the way the quantum state as being a lack of knowledge of an underlying ontic state. So it brings out the idea that it is accepting mind-independent facts. It's just saying that the wave function is not a property of those mind-independent facts. The psi-ontic view includes wave function realism within it, but actually is actually slightly different to that. It just says that a given quantum state preparation, will pick out distinct sets of states in the world. So two distinct quantum state preparations will pick out two distinct sets of physical states. So there's some property in the world that quantifies corresponds to the wave function psi or phi, but it's not actually a literally true picture. It's not a literal reading of that wave function as some sort of wave in a configuration space. It's just supposing that there is some property of the world that is being picked out by those preparation procedures. And of course, we'll pay attention, there may be hidden variables as well. Okay. So the key argument now goes that actually we can now do this kind of ontological models, no-go theorems analysis to actually distinguish between the psi-epistemic and psi-ontic point of view. Now, I'm overrunning on time massively, so I'm going to have to steam through the technical parts of this talk. We can gain access and we can actually gain empirical access to this distinction between a psi-epistemic and psi-ontic, because it plays a key role in the idea of quantum state discrimination. If we have two quantum states that are not orthogonal, then they cannot be perfectly distinguished. Your best guess, if they cannot be, and that seems puzzling if they are actually distinct physical states, or they're picking out distinct sets of states of the world, because in that case you ought to be able to distinguish them, you would think. So the psi-ontic point of view has to explain this in terms of limitations of all possible measuring devices. Whereas the psi-epistemic view, the view that says that the wave function is not actually a real property of the world, has a natural explanation of the fact that non-orthogonal states can't be perfectly distinguished. It has a natural explanation of this in terms of overlapping probability distributions. If you've got two overlapping probability distributions, your best chance of guessing which one, you have two preparation procedures, phi and psi. You don't know which one was used to prepare the laboratory. You have to guess on the basis of what the physical state is, or whatever measurements you can perform on the physical state. Well, your best guess of chancing right, even if you've got the best possible physical measuring devices, is given by this overlap here. Is the larger the overlap, the less chance you have of guessing right. And this is actually an operationally accessible quantity. But quantum theory actually gives, now the epistemic point of view actually suggests an explanation for this in terms of this value B. It doesn't just tell you that there is some limitation. It actually gives a value for how what our limitation is for making a best guess of which one of two quantum states was prepared. So the quantum best guess turns out to be this case. So if I prepare one of two quantum states and I put them in a box, put it in a box, hand it to you and say, you know it's one of these two states, but which one you don't know. Do your best possible quantum measurements and try and guess which one I prepared. This is the best you can do. So the epistemic point of view says that this quantity is going to be explained by this quantity. Okay, well, with a little bit of rearrangement, we can actually say that this thing here is actually can be related to experiment, the quantum distinguishability. So we can actually turn this into a bound upon how much of an actual epistemic overlap there is between the preparation procedures. So we can relate this in such a way that if we get a quantity here, which goes between 0 and 1, if it's 0, there's no overlap, even though there is some quantum indistinguishability. And if it's 1, this quantity omega here tells us that all of the reason for the quantum indistinguishability is accounted for by the overlap in the probability distributions. And this is empirically accessible, though. Well, given that doesn't help, because so far everything we said gives us still an epistemic view, and the epistemic view looks pretty good. In order to get a problem for the epistemic view, we have to add in a third state. And why is this? Well, because if we look at this, if we take 3 states and we look at the bipartite overlaps, the overlaps between any 2 states, we note there's a relationship between the sum of all the 2-way overlaps and the 3-way overlap. It's a bound. So if you have a large 3-way overlap, you can have very large 2-way overlaps. If you have a very small 3-way overlap, you're actually much more limited in what 2-way overlaps you can have. So this gives us actually a set of inequalities that we can use. I'll move quite rapidly through this. We can actually turn this into an inequality where what we have is a bound here on the average of, we take one particular standard pair and we look at standard state and we look at its overlap with a large number of other states. And we find the average of the overlap with the other states is bounded by this expression in terms of the average of the overlaps between this, of 3-way overlaps between different states. I mean, this is just a basically set theoretic calculation. But we can turn this into a bound where we can show that as we get a large number of states, as long as this state quantity here is small, the 2-way overlap is going to go as 1/n, and that's going to go to 0 as we have a large number of states. Now, of course, we've got an n here, so this is going to go up. So we need to make this very small. Okay. We can then plug a bit of technical detail in to actually get an expression for what the 3-way overlap is in the same way as we get into the 2-way overlap. I'll just move through this rapidly. We can also make the 3-way overlap experimentally accessible as well by measuring a property known as anti-distinguishability, which is where if we take any 3 states and we perform a set of measurements, if we take some diagonal, if we sum these 3 terms in a diagonal, then the 3-way overlap has got to be actually less than or equal to this. Sometimes you can even do better than that. So if we can find states which make this 3-way overlap very small, then we can, and even when n gets large, we can show that this is going to become very small. And the summary then goes, well, yes, can we do that? The answer is, of course, yes, otherwise I wouldn't be giving the talk. If we can get omega to go into 0, what we end up is with a proof that there is no overlaps between these preparations. So that becomes a proof that these states are psiontic, that psi is picking out unique states of the world. No, that psi is picking out distinct states of the world, distinct sets of states of the world. If, on the other hand, omega is always 1, then we'll actually find out that the epistemic view is very powerfully confirmed. So can we find states for which it goes to 0? The answer is, well, yes. We have a whole variety of states now, various families of states. And if we look at a graph of what these various different lines give you, is that as we get to higher dimensions at Hilbert spaces, we're generally moving down in the graph towards the bottom. So this axis here is the Born rule overlap. So here are states that are completely orthogonal, and here are states that are almost entirely overlapping in terms of quantum states overlaps. And what this percentage is expressing what this axis is expressing, what percentage of that overlap can actually be accounted for in terms of an epistemic overlap between preparations. Which means if we're up here on the top of it, it means maybe all of that could be accounted by overlapping probability distributions. If we're down here on the bottom of it, then we've essentially got a proof that the states down here have to be psiontic. And what we've got here is now families of states where, as the Hilbert space goes higher, gets larger, we find we head towards being psiontic. Now there's a limit here, because obviously it's only for states that have a Born rule overlap of more than between 2/3 and 1/3, or more than 2/3, that we get psiontic in the limit of high dimensional Hilbert spaces. So there are at least constructive models that sit somewhere around here that show that there are at least some possibilities for psi epistemic states, but there aren't anything that seems to work in high dimensional Hilbert spaces to my knowledge so far. So we've got a sort of halfway house here where we know that not everything can be accounted for in terms of epistemic overlaps. At the same time, in high dimensions, there's significant fractions of the Hilbert space that actually goes psiontic. Okay, so the psiontic claim then is that in very high dimensional Hilbert spaces, states become psiontic where Born-Wall overlaps greater than a third. Any credible attempt to treat quantum theory as the fundamental theory of the world must invoke one big Hilbert space of very high dimension. And going to this kind of psiontic limit implies that the preparation processes are picking out distinct states of the world. So even if the quantum state is initially supposed to be just this label in an operational framework, it seems to be picking out something distinct physical states of affairs. Each value of the quantum state is corresponding to some property that's being picked out in the world. But this analysis of this inequality didn't use quantum theory. Quantum theory just told us where to look for to get this omega going to zero sets of measurements, these preparation procedures. So as long as future experiments produce the same results, the conclusion remains that these preparation procedures labeled by the quantum state are still picking out distinct states of affairs. So any future physical theory must still include the quantum state as a possibly coarse-grained representation of the structure of the stuff of the world. So that's the thing that I've rushed through the technical results to try and get to this claim that I want to motivate. Any future physical theory must include the quantum state in any possibly coarse-grained representation of the structure of the stuff of the world. Now, this is different to the traditional no-go theorems, which are all making negative claims. This is what makes this one interesting, possibly for scientific realism, is because this is making a positive claim that future theories will have to be realist about psi. Right. So what exactly does this, can a realist use this? Is this really too good to be true? So the first claim is, let's say we have empirical grounds to believe the wave function is rule. Will any future theory must include it? Well, I mean, this is probably rushing a bit fast for the state of play. The existing proofs are certainly not perfect. The existing proofs show that the psi epistemic view fails to account for quantum indistinguishability and fails on one of its key motivations, but it's certainly not a full psiontic proof. But on the other hand, there is actually a more interesting claim, is that we've got a mode of analysis now that can, at least in principle, could show us how we could get evidence for realist commitments. And I'm going to argue that actually the theory change in theory choice programs is just blocked from the start, that these objections are just already off the table for this kind of analysis. Suppose we did have a full psiontic theorem. We're not arguing that we should believe in the reality of psi because of the predictive success of quantum theory. This is not the same as the traditional arguments for realism. What we're arguing is we've got a model-independent claim that, first of all, any future theory must attribute some kind of reality to the quantum state, because we're identifying the quantum state from a set of operational procedures. So the pessimistic meta-induction seems to be blocked. And we're also arguing that all empirically adequate theories must share this property, so the underdetermination argument is blocked. Now, it doesn't support a literal wave function realist view. The psiontic view is different from literal wave function realism. It says that distinct quantum states are distinct properties of the world. So when we're performing a preparation procedure that we label with a quantum state, we are genuinely picking out a property of the world. Now, there's a lot of possible physical states that could share that property. It's not committing to a particular fundamental ontology, it's committing to the wave function being a possibly coarse-grained property of whatever that fundamental ontology is. Hence, it's not literal wave function realism. But the quantum state, yeah, there may be more fine-grained entities, maybe more fine-grained structure. But the unitary dynamics that we use in quantum theory is coupling to this particular wave function property. Even if quantum theory is not the final theory, and we may discover more fine-grained structure, this won't get rid of this property from the ontology. So it's more on the lines of, we believe in atoms, even if we don't believe in indivisible atoms. We may not have got the details right, but we still think there's some structure in the world that corresponds to the wave function. Okay, loopholes, because there's always loopholes. Theorems and experimental tests don't yet prove this. We're still certainly subject to experimental testing. We know there are constructive examples of psi-epistemic models in small Hilbert spaces. We can only get a psiontic theorem in a limit of large Hilbert spaces. Well, yeah, maybe if we actually do test these psiontic theorems in large Hilbert spaces, it'll break down. So it doesn't necessarily give us a reason to believe right now that the wave function is real. In that case, if quantum theory turns out to be wrong in the limit of large Hilbert spaces, maybe the wave function isn't real. So there's definitely an empirical loophole still sitting there. It's not like I'm claiming we've proven now that the wave function is real. On the other hand, this is, if the experiments are successfully performed on large Hilbert spaces, this loophole can be closed, which does at least give some hope to the scientific realist, because it proves that in principle, the reality of the wave function is empirically accessible. So the argument that we can't get empirical access to these kinds of properties, I think is still being undermined. The very fact that we could do an experiment is our reason to say we can get experimental access to these kind of ideas. Further developments, well, one way out of this perhaps is to actually just construct better psi-epistemic models to push the boundary and show that no, really, there are good psi-epistemic models. That would certainly work against the idea of wave function realism. It wouldn't necessarily undermine the claim that this kind of ontological models analysis could in principle yield support for a scientific realist position. We could push further actually exactly what is being assumed in the ontological models approach. It's not completely model independent. It does incorporate some screening off assumptions. I sort of emphasized, if we just take the observed relative frequencies, we can always plug in a lambda and then sum over it. And we can always conditionally factorize it. There's an assumption here is that this lambda is a screening off. It's what's in the lab between Penny leaving and Mary entering, and that anything between the preparation and the observed outcomes has got to be screened off by some lambda. So it's actually a screening off condition the ontological models is incorporating straight away, and this could be denied. So retrocausality or an assumption of non-Markovian dynamics is certainly something that the ontological models framework has actually written out. So maybe there's actually further problems there. Maybe there's if you are attracted to retrocausality or to non-Markovian dynamics, then yeah, you can certainly deny this. So that possibly there is an argument for further underdetermination. Or you could just simply reject the ontological models framework altogether. You could deny the very existence of ontic states. This does kind of put you in the position of actually rejecting metaphysical realism, rejecting the very idea of mind-independent facts. Obviously, this is impossible to refute, but that's just external world skepticism is impossible to refute. You could accept the existence of mind-independent facts, but deny we can reason probabilistically about them. From a sort of a Bayesian perspective, for example, probabilities are all only Bayesian degrees of belief. I have no degrees of belief about things that are unobservable, therefore I shouldn't actually put a probability distribution over ontic states. I mean, I worry about these kind of rejections don't seem to be an argument against the scientific realist. They're just statements of prejudices against scientific realism. The traditional problems for scientific realism was that there were these theory change and theory choice and arguments that undermined the very reasons to believe in the first place. These are rejections of the reasons to believe, but they don't undermine the scientific realist's reason to believe. So, conclusion. I think there is a genuinely different mode of analysis here in principle. Whether or not it gets it right on any specific details, whether or not this particular argument is going to succeed is another question. But the mode of analysis actually in principle opens a different possibilities. Traditional no-go theorems have negative conclusions, but that doesn't mean they have to be. The Scientology theorems at least point in the direction of we could ask the question, do all future theories include certain properties in their ontology? And if we can ask that question, then we have perhaps grounds for scientific realists to sort of just shrug off theory change and theory choice arguments. It certainly doesn't give us unimpeachable certainty. It can only say we have reasons to believe. It can't say we have proven. And it certainly doesn't give us the kind of literally true picture of the way the world is. The best it can do is a claim that a coarse-grained structure must include something. But it does say, perhaps, that a scientific realist can claim that they have reasons to believe in unobservable properties that are immune to the pessimistic meta-induction and the underdetermination arguments. And so the anti-realistic doubts about these particular properties would seem to be relegated more to the level of general skepticism. Okay, that's my talk.
Thank you very much for the talk, Owen. That's great. There are many questions. So I see already. So Alexei, please. And just either raise your hand or maybe write your name in the chat so it's easy to see.
Yeah, thanks, Owen. I'm wondering what you make of all these recent debates around Wigner's friend, the experiments and the theoretical debates around it, because there is a very bold claim advanced in a series of publications saying that these experiments show that facts are, well, let's not say mind-dependent, but at least observer-dependent. Right, and that runs counter to the very framework you're presenting is operational, right? Because the kind of setting with two Wigner's friends will not fit in your planetary Mary framework.
Yeah, I mean, some of the, I have to say, I'm not as familiar as I'd like to be with some of the details of those recent arguments. In terms of what I have looked at, it seems to me that those arguments are building their own further assumptions in that certainly you aren't compelled to support. So the claim that certain facts are mind dependent, etc. All of those cases can be dealt with in terms of things like de Broglie-Bohm theory. I mean, none of these arguments actually get around the existing known interpretations that deal with the Wigner's friend type problems in a very straightforward way. So the strong, I find myself very skeptical about the strong claims that are made by some of these papers, I'm afraid. But I can't really say I've gone into those particular papers in enough detail to give a straightforward response to that, I'm afraid. Yeah, it's interesting.
Thank you. Then we have Lev, please.
In a sense, maybe it's a semantic question. I just want to understand if I'm scientific realist or not. I don't believe in any hidden or whatever variables. I don't believe in any observables. I only think that the only reality is a quantum state which never collapses. So I feel that there is something independent of my mind, of any copies of my mind too, because I have to accept that there are parallel worlds. But the only thing, the only reality, the only ontology is a quantum state. Am I scientific realist or not? Because it doesn't fit to the scheme which you presented.
So yeah, how that fits into this sort of ontological models is kind of an interesting one. From what you say, I would think you're a scientific realist, Lev, unless you feel you don't want to be identified as a scientific realist. But I think the question of how the many worlds and Everettian type ones fit into the ontological models framework is actually kind of it is a bit intriguing. It's certainly not the most natural fit. It is. You have to deal with how probabilities work in the Everett interpretation, and as opposed to how probabilities are supposed to be working into the ontological models. It doesn't seem to me that it's actually incompatible. It would the ontic state would simply be the wave function, though, and so it's going to work that way. Quite possibly what you'd be talking about here is it depends really whether you want lambda to be applied to the wave function of the universe type argument, including, say, the branches of the universe which the current portion of you that is talking is not part of, or whether you just want lambda to be the branches of the decoherent universe that Penny, Mary, and Terry are actually individually on.
Clearly,
in which case you could probably, if you go with the second way, you could
no. Second way, it's not the ontology is a universal wave function. I can take about some kind of subjective ontology. I can talk about what's inside the world, but this is not ontology. Just for me, this is very subjective. This is really for an observer. It's like average relative state or something. It's not. It's just for me. It's not something ontological.
But it is an objective fact that you are in that state and interacting with the world in a particular way. I mean, you objectively do undergo these decoherent processes and have observations and see the outcomes of the experiments.
I don't like the word decoherence. It's very not important for many words, but part of it, of course, it's important for me. And I talk sometimes when I talk for myself, and there is a backward wave function, which may be sometimes interesting inside my world. But to explain physics, I need physics explain everything. So ontology, it's about physics. So it's only about all words together. Then I can understand the illusion of non-locality, illusion of randomness, illusion of all kinds of things, because there is no such thing. Wave function is deterministic and without action at a distance. And then it's a good physics which can be relativistic.
Okay, but this isn't really incompatible, because it's like my claim is that actually we can believe that the wave function is real. So, I'm not sure you should be unhappy with that claim. Maybe not with the way I got to it, though.
I suggest you just move on because there are a lot of questions. So please, David, please.
I'm thinking about the kind of approaches to Bohm's theory that treat the wave function nomically. How would you think about that kind of framework in the context of these results?
Yeah, so the ontological framework is really not very friendly for the sign-nomological approaches. In terms of the way it sort of categorizes things, any attempt to basically it just dumps that into the psiontic type approach. You'd have to look at a more wider thing. I mean, it depends on how the details of how the sign-nomological approach is then supposed to work out. I mean, if you're just supposing that psi is something over and above that is like a time-dependent Hamiltonian that sort of exists and evolves in some sort of universal relation, perhaps, with just a nomic status, that, yeah, the psi-epistemic psiontic division is going to pick out anything like that and say it's ontic. Similarly, I mean, just as much as if you had a classical Hamiltonian system and you had a time-dependent Hamiltonian that had degrees of freedom to it, and you did the analysis, this analysis would just simply dump that Hamiltonian as being ontological. So it's possible that, you know, that a psiontic psionomic division is something, a more sophisticated division that can be picked out. But remember, the claim for the psiontic here isn't that the wave function is an entity. The claim for the psiontic is the wave function is a property. So perhaps actually like the Hamiltonian or the wave function being properties is the right way to think about that.
I wonder if the stakes are slightly higher than that. I mean, not just in the in terms of the psiontic framework, but in terms of the scientific realist conclusions you want to draw. I mean, there's at least one reading that says, look, what this should tell us is that even if there's some sense in which the wave function as a whole, the universal wave function is gnomic, then I really do need to think about the ontology of my particular system as including the particle relative wave function of that system. And I can't just think of the ontology of that system as consisting of the particles and nothing else. Or conversely, if that's not the case, if we are allowed to say a gnomic reading of it is a kind of get out from saying we've established that these are real properties, then you want to worry about whether that undermines the kind of we've established these are real features of the system, irrespective of future science. I mean, I read the argument you're giving is actually quite a good route to say that even if you want to be synamic at the universal level, these are real physical properties, and you're not really fully describing a Bonian system by saying it's just some particles. But if that's not the reading, as I say, I wonder if it cuts against the scientific realist conclusions you want to draw.
Yeah, I'm not sure. I think my actual response is I would actually feel that that kind of strong claim that's entirely synomic and trying to actually remove any kind of ontic properties to the wave function, I don't think fits very comfortable with the argument I'm putting, and I do think it suggests that we have to think of the wave function as being a property, not some, in a way that's more than just some purely nomic entity.
Yeah, and that was my impression too. I thought you can repurpose your talk among other things as making a really rather good case for that. Thanks.
Please.
Thank you for that comment. Yeah.
Thank you. Please, Aurelia.
Yes. So thank you for your talk. My question is related to first maybe to the semantic. I'm not really sure that the distinction between epistemic and ontic is always very clear, especially in a context of Bohmian mechanics, because if you speak about probability, it seems for you that is that it means something of epistemic, but it can be also something completely related to the initial conditions. Then it's not really more so much about knowledge, but about objective facts. You know, so this is okay. This is a debate about the what is probability, but my question is also related to the fact that you use the formalism or the language of Speckens, and I use also in the PBR theorem. And so I could have some questions if this is your derivation is using all the same argumentation, because the details are not completely clear for me. Maybe I have to read some of your manuscript on that. Maybe you have a paper written, because cannot follow, but it seems that you're using the same kind of reasoning, and so it means that your definition of conditional probability, for example, when you say you want to detect you have to detect an event knowing that you have a hidden variable lambda, is independent of the wave function, it seems. And it was an assumption used by PBR theorem. So if it is the case, then Bohmian mechanics is not fitting in the framework, and I have an issue with this. But yeah.
Okay, I'm not completely following. I mean, it's not. It's not an assumption that lambda is independent of the wave function. There's no assumption there. So I think in terms of the PBR theorem, for example, even in the PBR theorem, they don't assume that lambda is independent of psi. Where psi is now just interpreted as the label for the preparation procedure, because for a given psi, there is supposed to be some stable probability distribution over lambda. And then that is a substantive assumption, and it's a probabilistic assumption, and certainly there is a questionableness over what interpretation of probability is going on there. As I said, there's definitely a very strict Bayesian may well be inclined to doubt whether you can construct a probability distribution that way. It does seem to sort of imply some sort of chance kind of function or something like that. So there's certainly definitely assumptions built in there. I freely have taken the ontologicals framework from Robert Speckens, which partly because my original motivation was looking at the psi-epistemic psiontic division that Speckens puts forward. So I wanted to just take the formula framework as given by Rob, so he couldn't complain that I'd put something in there that he didn't agree with. Yeah, I mean, I think there's definitely possibilities for further development of that, and that also goes with, for example, seeing how things like Everett, as we talked earlier, fits into that kind of framework. It's I sort of hinted at that on one of the slides and saying actually there's a screening off condition, for example, going on there that's been assumed. So there's certainly grounds to say that there's actually a lot more in there that could be doubted, and that points in the direction of worries about underdetermination type arguments, for example. But I would like to be convinced that those grounds are actually really strong grounds, because most of the claims that the ontological models framework is insufficiently general, I don't find them terribly convincing, because I find that you can usually incorporate the examples. It's rather that there are limited presentations of the ontological models framework. But I think that's an area just for further exploration and further pressing on the actual framework. But I think it's best if you actually do that by moving outside of the specific no-go theorems and actually just looking at the more general claim of, well, what would an ontological framework be that goes beyond just looking at quantum theory, that goes on trying to look at scientific realist claims, perhaps.
Does your work has been published? Because I would like to read the details and I don't know.
So the specific scientology proofs are in the literature. So the main one is Barrett, Cavalcanti, Lam, Maroney would be the one that I would point in the direction of, and then there's ones that cite that, and ones that it cites.
Okay.
And that goes back to about 2013, 2014, the actual proofs.
Okay. Okay.
So now we have Carl, please.
Thanks for the talk, Owen. It was really fascinating. I really liked it. I just wanted to get some clarification about what you're saying that we might be forced to be realist about. And so let me lay out how I was understanding the story. You said at some point that quantum mechanics isn't really presupposed in the derivations. And I take that to mean we're not appealing to any of the things like the Schrodinger equation or other laws of evolution or any of that kind of details of quantum mechanics. But at the same time, the slide you had showing us where we may be forced to be realist talked about Born rule overlap. So there's definitely this idea of the Born rule that's built into this story. And so I gather that what the argument is aiming towards is just the existence of something that you might call states of observables. And it's saying that you can't deny that psi gives us at least a partial but correct and true description of some things that we tend in quantum mechanics to call observables possessed by systems or something like that. But it's not going to satisfy the realist itch to believe in the truth of a theory, because we don't have per se grounds to take QFT or any other fragment of quantum mechanics to be giving us, as it were, a true theoretical story. Is that a good way of thinking of it?
I think yes. I think you've put your finger on one thing that I think in my presentation was unclear, which I might. So yeah, I had the slide that had the graph and it said Born rule overlap, and you're saying, oh, quite correctly, that's actually a quantum mechanical thing. So what's actually the claim here? Well, the claim goes that we have suppose we have two preparation procedures. And I prepare some system according to one or the other preparation procedure. Can you, then not knowing which preparation procedure used, can you determine which preparation procedure I used just by measuring the system I prepared? If you can, then it better be the case, then my preparation procedures must have picked out distinct sets of affairs. So in that case, you know, if not, my two preparation procedures are actually perfectly distinguishable by you, then there must be something distinct about those two preparations. They must be picking out distinct states of affairs in the world. So they must be latching onto something real about the world. It's only a doubt if that they are not. If you've got two preparation procedures, and no matter how good an experimentalist you are, you can't perfectly tell me which preparation procedure I did. So that's what we have with quantum theory with non-orthogonality. So that's the point where it says, okay, so we've got this experimental indistinguishability. Now, one possibility is we're just wrong about that, and we can come up with suddenly there's a very, very clever experimentalist who next century discovers a way of perfectly distinguishing what we previously thought was non-orthogonal quantum states. Okay, well, we were just wrong. Quantum theory was wrong. Fine. But suppose that doesn't happen. What this gives us is ability to still nevertheless say, even though we can't empirically distinguish those preparation procedures, we can still push it to a situation where we can say they must nevertheless still be picking out distinct states of affairs. So they must still be picking out real things. So those labels, psi and phi, that we put on those two preparation procedures must be labels that are picking out real stuff in the world. But that's as far as we get, right? So yes, the realist itch to actually then go further than that and say, and the world is thus and so, still has to be much more modest. The realist can only be very modest about this and say, okay, what I can do is when the anti-realist says, I can't get epistemic access to the truth of the statements of unobservable properties, the realist goes, well, actually, I can get some epistemic access to it. Maybe not as much as I'd like, not enough to scratch my itch completely. But you can't tell me that I'm just completely unable to make anything statements about these unobservable entities, because look, I can. So it's kind of, it's an in-between. No one's entirely happy with this situation.
So we're running, thank you. We are running a little bit late. So Alex,
okay.
So make it short, please.
I'll try to make it I'll make it very short then. So thanks for the talk. So if I make it very short, then I would just say that one of the main arguments against being realist, not only about the wave function, but even against the idea that the wave function refers to something real, to some real stuff in the physical world, is a measurement problem, right? The sudden change of the wave function, the pre-measurement wave function to the post-measurement wave function. So that's one point. And the second point, if you go to relativistic quantum mechanics, you also have like a propagation of the wave function outside the light cone. So this is also often used as an argument against the reality of the wave function, that it can refer to something real. So I was just wondering how these aspects fit into your framework. That's to make it short.
Okay, well, to try and make it short in response, I don't think being anti-realist about the wave function helps with either of those problems. Is the basic sort of response. The idea that wave function collapse is a problem for realism. I mean, the anti-realist still has to provide an account of it, and mere Bayesian updating is not sufficient because measurement must induce disturbance, and mere Bayesian updating doesn't involve disturbance. So an anti-realist still has a story to tell about the measurement problem, and of course, having denied. The anti-realist, I think, has a harder problem because they then don't actually have any model to explain what goes on for that measurement disturbance. Whereas the realist constructs an explicit model for it. And as far as relativity is concerned, well, I'm on the increasingly, I think, unpopular position that the Bell inequalities prima facie say that relativity maybe isn't fundamental.
Okay. Thank you.
Then please, Alexia, if you can.
Yeah, so I try to make it super duper short. Thanks, Owen. It's nice to see you in another context than the usual discussions with Oxford. So I have actually two questions that are based on an observation. So you started your talk with this very nice list of how to be realist and reminders on what realism is. But then I had the feeling, so maybe I missed a step, that you immediately introduced the quantum states as something like being psi. And I missed a definition with words of what you mean by state. And this brings me two comments. The first one is that I think it's very important, and I'm a physicist, but I like philosophy, as some of you know. I think it's extremely important that we are able to talk about quantum physics without jumping on the mathematical formalism right away. It's important for societal reasons. Quantum physics is becoming under the lights now, and we need to be able to explain something about reality. And the second thing is that I also have the feeling that your psi depends on systems, right? While there are alternative ways of defining quantum states that would pertain to systems and contexts. So I think about contextual objectivity. And so it's an advertisement flash for the roundtable of Wednesday. But so to paraphrase what Alex was saying, how does it fit into your context? Do you see ways of talking about ontic and epistemic states if you think about them being contextual?
So I think, I mean, you're right, state is an extremely overloaded word and we use it too rapidly without actually, but yeah, unfortunately, mostly I do it too rapidly because I'm trying to fit too much into my talks and I'm rushing over things. At the very least, there's two things going on here. There's the kind of notion of a preparation process and the state associated with the preparation process. And then I talked about, you know, there's the ontic state, which may or may not be the same thing as the quantum state. The quantum state in this talk is really meant to be nothing more than you have your operational framework and you have your preparational procedures. And then you discover there is actually some relations between your preparation and measurement procedures that turns out mathematically describable by this funny Hilbert space structure. And then the quantum state is just picking out the bits of the Hilbert space structure that you use to describe.
So you definitely need that in there.
Need that in there.
Okay.
Well, it's more actually you've got the empirical, you have the empirical data, and then you discover that the mathematical representation of that empirical data has this Hilbert space representation. I'm not sure it's in that sense you need it. It's actually it's what it's what makes that empirical data quantum theory and not, say, classical theory.
Okay.
Very good. Thank you again, Owen, for that. Thank you. I suggest we make a 5 minutes break now, and then we just reconvene with David Wallace talk at 5 to 4, let's say. Thank you very much, Owen, again.